All right, let's get started. So Thursday before spring break, thanks for showing up. Wednesday before spring break, you see where my mind is. So we just finished the kind of physics-inspired algorithms and simulated annealing. Any questions that come off of that before we move into something totally different? All right, so I mentioned, so there was a new, so you recently finished up that homework on general Pareto optimality versus Nash optimality, and I just put out a new homework that is on the actual Pareto, the multi-objective algorithms for solving for Pareto optimality. So you can check through that. It's just a couple of questions for topics, and then glance through a paper and answer some questions about that paper. And then I'll put out, there's still, I owe you a couple of questions for multimodal optimization, and then this new stuff on the nature-inspired maxent and simulated annealing. So all that's there. So I did add a midterm to the syllabus, and so what I decided to do for that one, because I didn't do a midterm last time I taught this, it was a little smaller, it was a different format, but I also, I wanted to kind of blend and compromise. So what I'm going to do is basically create, and I've started to create this, a Canvas administered 75-minute, take it one time, at home, open notes midterm. So it'll be one of these things where once I release it, which will be after spring break, you'll have a couple of weeks to decide to start it. It's kind of like renting a movie or something like that on Google Play or something like that. But then once you start it, you'll get 75 minutes. Or if you're got special DRC, then you've got whatever the DRC has that you get above that 75 minutes. And then you just, it'll be graded online, so it'll be a little bit like some of the homeworks. Maybe I push you a little harder, ask you to do a little bit more critical thinking. You won't get a whole lot of feedback on correctness or anything like that. So it's just meant to be kind of an assessment to get everyone kind of thinking about what they've got up to this point. So the stuff that, basically there'll be questions that as a researcher, if I were to show you these frameworks, it would be something that I want you to sort of immediately be able to recognize and pick up on. So I'm not going to ask you to do a lot of tedious coding or anything like that, but I might show you some pseudocode and ask you about it, or I might show you a Pareto frontier and ask you about it, and so on and so forth. So very similar to kind of almost a sampling of the homeworks that we've had, and I'm currently designing it to go up through simulated annealing and stop there. So that's the plan for that. So expect to see that sometime in the near future. What you did, yeah, questions?
So just so I'm clear, it's going to be posted and made available to take at your own leisure after spring break.
That's right.
Thank you.
Yeah.
But have you considered doing something similar for the final exam?
I have, and so I'm definitely evaluating ways to streamline things for all of us, because to me the value of this class is you guys have been you participated so well in class. And I've been liking the feedback I've been getting from students after the homeworks in office hours and such. And so that is already kind of satisfactory to me. And so I want to make sure that people focus most of their time on a really cool project. And so these are just mainly providing a little bit of extrinsic motivation for you to kind of keep up with what we're talking about in class. But then you can spend most of your effort on coming up with that cool demo of that, that really rad nature-inspired algorithm. So that's the plan here. All right. So then you also saw that, speaking of the project, I released those 3 kind of almost administrative assignments. There's one that's due, I think it's the week after, or maybe it's a Sunday after spring break or something like that. Maybe it's a Sunday of spring break, like the second Sunday. I might have gotten that wrong, but it's the one where you just say who's going to be your teammate, and everybody submits that. So every single person should have a submission that just says, I'm going to be on a team working with this person. And then that way I can double check that everybody's got the same teams. And then I'll create groups during that week. And then at the end of that week, as a group assignment, you'll submit your little choice of algorithm. And so if you choose one from the list I've given you, you just give me the name of what you want to study. If you want to come up with your own, you have to give me a few more sentences kind of telling me roughly what you're planning on doing and why it relates to this course, why it's relevant. Nothing's, just a couple of sentences, because then you'll actually write together the proposal, which will be like 2 paragraphs. The first paragraph on the algorithm you're studying, the second paragraph on your plan for the demo. And so those 3 deliverables you'll see due roughly within the 3-week period or something like that, or 3.5-week period after spring break. So those are all available now in case you already are ready to submit some of those. So any questions about that? All the administrators, yeah.
So the candidate algorithms link to, is a page not found.
Oh.
If you go, is another one that's on there. Just click on the
I can fix all of that, I apologize. So, yeah, when I imported it from Blackboard, I may not have caught all of the links, so I will look for that. But I think if worse comes to worse, if you go to modules, there's like a final project module, and you should be able to get it from there.
I see, okay, I got it, sorry about that.
Yeah.
Is there a limitation on the group size?
I want groups of 2. That would be ideal. Well, I mean, because I don't know if there's an odd number or an even number in the class, I think there might actually be an odd number that I may have to make some concessions, but I just worry that if you get even 3, things can get a little diluted in the, and I want to make sure it's like a grad level class, everybody feels like they're really taking a big bite of the apple. But if you've got a particular case to make, I imagine I'm probably going to have to allow for at least one three-person group. But if you're doing it, if you want to do a 3-person group, I would say you need to justify to me like, whereas the other groups, you don't have to do this, but I'd say if you want to do a 3-person group, ask me ahead of time and tell me what you plan for each person to do specifically, so I can kind of make sure that 1 person or 2 people don't just sort of get hanging on to the edge.
Could the group be just
I'd like for, if I allow for 1-person groups, it ends up just making, it ends up being very difficult for me to grade at the end of the semester to get everything back in time. And I think there is a little bit of value in this project to have 2 people, so I'd prefer, if you're having trouble finding someone, people have already, I think, posted on the discussion board. You can post on the discussion board saying, I'm looking for a member, I'm interested in this, and then hopefully try to recruit from that. Anything else? Yeah.
The counting, there are even number of students.
Oh, and here, yeah, but I think the actual roster might have an odd number.
I mean roster.
Oh, okay.
Online.
I see, gotcha. Well, so, shouldn't be a problem then. All right. Okay, any other questions? All right, so, like I said, we're shifting into something new, and I'm checking with availability, but I might even bring in a guest speaker the week after spring break during one of those days to talk about one of the applications of this. So we're moving into what I'm calling roughly distributed artificial intelligence and swarm intelligence. And so a big difference here is that we're talking about things like autonomous learning agents, or I'll say autonomous learning systems, and then within those systems, you could imagine, agents, or just like nodes on a graph, or something that we'll see kind of what we mean by that as we go on. These are distributed, so somehow information is acquired and accumulated and processed in a distributed fashion. There are going to have independently, that looks kind of right. Independently acting parts, possibly asynchronously. So I'm just going to say async. So they're not all marching in time. And then communication will be a big part of this. So they communicate, so I'll say communicate to share solutions. So when you combine all of these, kind of the inspiration for this is the strength of this approach is a loose connection between them. So their independence hopefully makes them robust to individual errors. So we are counting on this kind of wisdom of the crowd sort of thinking of this. Now there are madness of crowds as well. I have a colleague who did an experiment actually with ant colonies where they had to decide on 2 nests, and this particular colony likes the nest to be darker, and you can give them a nest that is only slightly darker than the other and colonies are really, really good at discriminating. So the colonies will move into that particular nest. But you can also test individuals. And it turns out that individuals are really good at the easy problem. So when it's really bright and it's really dark, they can find the dark nest and they'll move a bunch of brood into them. But if you test the colonies on the easy problem, they actually are worse than the individuals. So it's an interesting trade-off where there is some sort of Pareto curve here, and that as you aggregate these individuals together, you might make them better at some problems but worse at others. And this idea of making them robust to individual errors is sort of what's behind all of this, but you can still sort of say, well, what do we call an error? And you might actually make them more fragile to certain types of errors. So the errors you wouldn't normally think about, like, oh, it's an easy problem. Well, it turns out that if you have a bunch of individuals trying to solve an easy problem, there's the higher chance that at least one of them is going to just make a bad choice. And so that would get washed out if you're looking individual level statistics, but these communication solutions can sometimes accidentally amplify a bad choice. So you can get the groups to make bad choices on problems that they almost never would make. So you can actually amplify the error rate in some of these cases. So it's something to think about, like, do I really want a distributed framework? And maybe for easy problems, you don't want a distributed framework. But for hard ones, maybe you want as many eyes looking at that problem as possible. So it's just kind of a meta level thing here. And so this is what I'm calling kind of distributed artificial intelligence. And I would say it's closely related to this field of swarm intelligence. And sometimes sometimes the swarm part of swarm intelligence doesn't necessarily need all of these parts. And so there's different subsets of this go into kind of a looser organization of what we call swarm intelligence. And I'll kind of give an example of that in this first case here. So this is a header for a number of different things that we're going to talk about over the next couple of lectures. And just in this lecture, if we get through all three of them, we'll have three very different, but I hope you can see related ways to solve optimization problems with multi-agents, building up from one that's very popular to one that you may not have heard about, and to one that also is very popular but solves a very different problem. And my claim is you can kind of make a stair step from one to the other, and then you could imagine your own kind of spins on these things. So let's just, to get an example here, let's start with, so our first case here, we are going to implement communication among agents through modification of the environment. So communication by modification of the environment. And I guess I should make this insert maybe the word persistent, because you could say, like, well, technically I'm communicating with you right now and I'm modifying the environment. There are pressure waves that are moving centered on me as a point source and going out to each of you. And they are creating changes in your cochlea that are being transduced and eventually being processed by your brain. But that is a transient change to the environment. And so the thought is, can we actually make persistent changes in the environment that create a longer term coordination among agents? And before I answer the questions, I just want to put this term out there. And this is broadly going to fit under this, you may have seen before, this heading of stigmergy. And so this was a term that was first popularized in a French paper, I think in the 50s, about termites. And it has since been used since then to basically mean coordination by persistent modification of the environment. Now, I saw a couple of questions.
Yeah, I'm sorry. So I just missed out. What are these cases all about?
Well, okay, this is, I would say these are examples of what I'm calling swarm intelligence, which I'm viewing as kind of a broader set of distributed artificial intelligence.
So this case, when you talk about modification of an environment, so individually they contribute exactly how?
Well, and maybe we'll see that as we go through this first example here. So I'm going to go through what's called ant colony optimization, or as I presented its original form, which was ant system, which shows how the environment is actually a computational environment. But if you're building a robot, for example, this could actually mean structuring things in a particular way. So in the case of termites, for example, the thought was that that maybe a termite doesn't quite know what to do, but it bumps into structures that were built by other termites, and that provides a cue for what it should do next. And so even though it's not like it's not like I went out and said, all right, what did you guys do? Are you built the stairs? All right, so I can go and build the deck. So instead, it's like I bump into the stairs. And I say, oh, there's stairs here. I'm going to go build the deck. So that's sort of the idea of stigmergy, is that we are not communicating directly to each other. We are indirectly communicating by modifying the environment. Another question?
That
Yeah.
answer.
Okay. Great. All right. So, yeah.
But the different swarms have different behavior.
That's
like
right.
ants, bees,
Mhm.
worms. They
Right.
behave differently.
Right. Right.
But which one we are talking about?
Well, so this is a general category that we group robots into, we group algorithms into, we group, but not, so but like you could say that termites do this, but they don't have to do this. This is just one strategy that they make use of. And the claim is that normally when we engineer systems, especially physically embodied systems, we don't make use of this principle because we don't know what environment's going to be there. So if we can't count on the regularity of the environment being our communication channel, then this is a dangerous strategy to depend upon. So instead, you say, rather than me assuming that I'm going to have enough material around to structure in a way that coordinates all of you, I am just going to come up with a language and a modality to communicate that language. Maybe I send it to you via Wi-Fi, or maybe I send it to you via a sound or light or whatever. And then we always can count on light being available. We always can count on sound being available. So when we don't have to worry about these kind of long-term effects. So I can talk directly to you, and I don't need to worry about the words lingering there and depending on them from them being there for the next 10 minutes. I kind of assume that once you hear me, then it's taken down, and it's fine if the pressure waves dissipate. And so, but in stigmergy, you assume that there's actually going to linger in the environment, and that lingering is what actually ends up coordinating the agents together. So, and it is a one strategy. Across the 15,000 species of ants, some use stigmergy to coordinate foraging, others do not. So just among ants, you see it or you don't see it. You can build algorithms, some that use it this way. This computer scientists would view often as like making use of a shared memory. It is much more difficult to write formal proofs about the correctness of algorithms that use shared memory than it is algorithms with just peer-to-peer communication. So usually this is often avoided because it's difficult to sort of keep track of the state of the physical world, because the state of the physical world accumulates the history of all of your agents. And if you have 1,000 agents, there's a lot of things that can happen to the world. So how do you write a proof about that? So that's why oftentimes these strategies are avoided if you're in a formal methods community, which has become an issue because now the formal methods community, which largely a big part of this distributed algorithms community, are interested in reasoning computationally about things like ant colonies. And they are now pushing computational frameworks meant for robots onto ants when, say, ants don't have any business using those frameworks, but they're just the easiest ones to reason over. Yeah.
Are there any theoretical papers that you know of that are using this stigmergic coordination that actually have managed to prove something about whatever their algorithm is?
Well, I mean, so I would say that there are plenty of papers in the distributed algorithms community that attempt to get a grasp on shared memory. And my claim is that you probably could look at them through a stigmergic lens, even though those authors probably weren't interested in describing them that way. So yeah, if you just want to say, I would Google, like, if in the formal methods community, just look for shared memory, and I think you'd find a bunch of things that you could probably argue are swarmy.
Okay.
All right, so our example here is something which the modern version is known as ant colony optimization, or ACO. So you can find ACO as in a drop-down pre-made algorithm in a lot of your favorite numerical tools out there. It is an optimizer that is almost as popular as things like the genetic algorithm. It originally was called Ant System, in the first paper that was written about it, but that didn't quite mark it as well, I think, as they wanted. And so they modified it a little bit, but then they turned it into ACO. And so 3-letter acronyms are always better than 2-letter acronyms. So yeah, so it's, I mean, I don't know, the genetic algorithm, I guess, is a counterexample of that. But the idea here is, we said, okay, well, we would like to solve a combinatorial optimization problem. And so the idea here is I've got a certain number of decision variables. So I'll say I've got decision variable, and I'm just going to number them like 1 through capital N. So 1, 2, all the way down through capital N. So each one of these are decision variables. And this is a discrete optimization problem. So each one of them has a discrete value, a set of discrete values that it can take. So I've got value 1 for decision variable 1, value 1, or value 2 for decision variable 1, all the way through, say, value D for decision variable 1. So this is supposed to say D sub 1, so it's like the number of levels that decision variable 1 can take. And then you can also then do that for all the rest of them. So decision variable 2 has got its own set, and it may have a different set of levels. So this is V2, D2, and then all the way down through decision variable N has got a number of states. And so you've got all of these things, and you want to optimize over this discrete space. And so imagine there's a lot of decision variables and a lot of states. And so this would be a complicated combinatorial problem where you could say, all right, I'm going to need to try every one of these. I'm going to fix this one and try every one of these. And then I'm going to fix that combination, try every one of these. And so it's a combinatorial explosion if you want to search the entire space. And is there a question?
When you say limits, do you mean dimensions?
Well, I would say that, no, I would say the n, these are sort of dimensions, there's n dimensions. And then, but this direction is not level, but this would be, so instead of this being an interval that I could optimize over, I'm just saying there are capital D sub 1 different samples of this interval that I can choose from. So rather than saying, so this is x1, decision variable 1, in a continuous problem, I would say x1 could be anything from 0 to 1. What I'm saying here is that x1 can be any one of D sub 1 levels. So it can be 0.1, 0.2, 0.3, 0.4, 0.5. It can't be anything in between.
Discrete values.
So it's discrete values. It can be m discrete values.
So it's the set that is possible for decision variable.
Yes, that's what D1 is. D1 is the number of choices you have for decision variable 1. So D1 times D2 all the way up to times Dn, the product of all those, that is the number of different ways different solutions that are possible. So if this was a continuous problem, we could use calculus to guide our search. And so Marco Dorigo and I think one of his students at the time said, how might a trail-laying ant solve this problem? And it's unfortunate it's called ant colony optimization because there are lots of ants that don't use trails. Like you could have called it trail-laying ant colony optimization or something like that, and then we could call it TLACO or something like that, and it would have a nice ring to it. But instead, it's just called ant colony optimization. So now hordes of computer science students assume that's how all ants work, all because Marco made this choice. But so that's fine. That's a different sort of story. But so then what does this do? So imagine if each one of these things are like locations the ants could go. And then each one of these are locations where the ants could go next. So you could imagine one ant could visit this location, and then visit this location, and then visit some other location, and then visit some other location. And so some ant would form a path where maybe it goes from here to here, it stops at some other location here, and then comes back, and it ends here. So you could imagine maybe there's a nest here, and then the ant goes out, and then maybe it finds food over here, and then it can come back that same route there. And you might imagine the ants might be solving a problem like, how can I find the shortest path through these different options? And so I travel to this island, and then I travel to this other island, and it's really costly to move from island to island, so I'd like to minimize the path between these islands and then find a path here. So it's like a traveling salesman problem. And so, so how would a group of ants individually search this space and then coordinate with each other so they can share their collective success and gradually find among all of them the best path? And a bonus, in case that best path gets destroyed by something, so if somebody makes one of these options go away, how do you maybe keep track of the second best path and the third best path so that you can fall back onto those very quickly? So that was the motivation behind this. And the thought was that I would have then run a bunch of agents in parallel, and each one of those agents is going to go down a path drawn randomly in a particular way. And based on the objective function that is evaluated using this solution, this candidate solution, so this, and this, all those put together, that's one candidate solution, it's going to lay a certain amount of pheromone on this path. And that pheromone will be observable by all the other ants. And they will adjust their choices based in part on how much pheromone is laid on these choices. So initially, they all effectively search everywhere, and then gradually, based on the objective function, a few paths become very attractive, and all the ants end up investigating them as well. So, so how does that work? So we're going to need basically two. Yes. So pheromone is, that's a term. So you know you have hormones, and those are chemical communication systems inside the body. And a pheromone is a chemical communication system among individuals. And so it is just a chemical that allows one agent to talk to another agent. And in this case, because we're using stigmergy, we could imagine smearing a pheromone on the ground. And then even though I walk away, it still smells like me over here. And you can imagine spreading different types of smells. This is an attractive smell, this is a repulsive smell, and so on. And others can reinforce that smell, or maybe they could cancel that smell out. And then you can imagine each one of these smells decays over time. So even though you put some mark there, if no one else reinforces it, over time it disappears. And it is that balance of how often do these things get reinforced and how quickly they dissipate that makes this algorithm work. Yeah?
Okay, so essentially we're trying to find the ideal set of decision variable choices which will give us an optimal result, right?
That's right.
So I'm just failing to understand how there's a path which we can come across. I mean, it's kind of like a brute force approach, isn't it? You choose any choice, so where can you exactly get a connected choices?
Well, so brute force, that's, so brute force would be doing the first thing where I say you try everything. And so in this case, you initially explore everywhere, but on the way to trying everything, certain good solutions will become more attractive. And so these paths are fictitious. They don't exist in the optimization space. These paths are really an agent decides on level 1 for decision variable 1, and then it then needs to choose among the D sub 2 levels for decision variable 2, and initially it just chooses randomly. And it's like a spider web, now I'm mixing metaphors here, where the spider is dropping a line and it's connecting each one of these. But gradually that line accumulates and attracts other spiders to it. Oh, now we have spider colony optimization. So SCO. So that, but it's a similar sort of idea. So maybe if it's easier to think of agents dropping lines behind them as they move from one decision variable to another, that's where this path comes from.
So if we are choosing everything randomly, then the chances of a path being preferred over
It's
others.
initially random. And so let me get to the next step here, and we'll see how we get rid of the randomness and bring in the optimization function. Okay, so the essential features here is that we are going to have, maybe I'll put this in a different color. We are going to have some decay function, and we will have some deposition. based on optimization objective. So let's introduce a concentration here. So we can say that each one of these nodes, I'm going to build a node-based algorithm. You can also build algorithms based on links. So I am going to put pheromone on the levels as opposed to putting them on the links between levels. But you could just as well put them on the links between levels and define your algorithm that way. So that's kind of like the edge graph or something like that. And so, so I'm going to define a concentration at each individual node. And that concentration is just going to keep track of how much virtual chemical is on that node right now. Yeah.
Is there one that's more computation efficient, or they are equally efficient? I mean, the node and the edge one, are they computationally the same, or?
Well, I mean, I think it's probably going to depend on the problem. Yeah, I mean, you can kind of see that I've got 3 nodes here and 3 edges, and so already it seems like it might be a wash, but but the dynamics I think will definitely change. So I guess, yeah, if you imagine that it's important to keep correspondences between these, then maybe that's the reason why you might want to smear chemical on the edges, as opposed to keep track of just which the individual nodes are. Because right now, if this is a really good path, I am going to end up putting more pheromone here, and it's going to reinforce this one, but it's not going to give me any insight that I need to go to this one next. I'm just kind of counting on that whoever is smearing chemical here will also be smearing it there. So putting on the edge naturally creates a coupling there, but it doesn't create a coupling between this edge and this edge. So yeah, I am not prepared standing here without doing a little more research to answer that question.
I mean, if I put pheromone in the nodes, I'm gonna do the path, right? I mean, if I can guide them also through the nodes.
Right, yeah, I mean, so each agent is going to smear pheromone on each one of these.
Okay.
And so effectively they're smearing it on the whole path.
Okay.
Yeah. Uh-huh.
What's the coding equivalent of pheromone? I mean, you can say that it's sparing pheromone when I'm writing a code, whatever.
Right, this is what I'm about to write here. So I define this concentration, which is just a variable. So you have to think about the space complexity of this algorithm. You have to keep track of a state variable for every one of these levels. And that state variable is this concentration. And so you can imagine that this is like concentration. Back here, all right, good. Concentration on coordinate, I'll say I, comma D. So that's but I'm going to put a little tick here just to indicate the next value of the concentration. So this is next value in my algorithm, and that is going to be equal to some say 1 minus rho times the previous value here, and I'm going to add something with the objective function here. So already you can see just in this part I have a naturally decaying. So if I start with some value of the concentration here, if rho is between 0 and 1, then the next value will be a little smaller, a little smaller, a little smaller. And so gradually the concentration goes to 0 if no reinforcement is put back into play. Then I add to that, and I'll write this as the sum from j equals 1 to m, where there are m ants. So I'll say m ants, n variables, and m ants. And so for each one of those ants, it then calculates how much additional pheromone to add. And so for now, I'll just put this as, call this delta C I D, and maybe I'll put a little superscript just to make things more confusing with the J up there. So this is how much this ant decides to put on this particular node. And that can take a lot of different forms. So let's just say that I want to do a minimization problem. So one potential form, for example, for minimization, is me trying to write minimization. Then I can say, well, maybe delta C I D J will be equal to some quantity of pheromone that I could lay, Q, divided by the optimization objective, evaluated, say, along that path. So that optimization objective, so maybe I'll put along my path xj. So this decision vector is my evaluation of my path. And so I go through the whole path and I calculate how big this is going to be. And if it's a giant value and I want to do a minimization, I'm going to take all the pheromone I could smear, and before I smear it, divide it down. So I'm going to dilute that, and then I lay a tiny amount of pheromone on each node. Whereas someone else that finds this is closer to 0, again, I'm doing a minimization, let's say this is just positive, is going to lay a lot of pheromone. So ants that find a path that is at a lower value of F is going to lay more pheromone, and ants that at a higher value of F are going to lay less pheromone. And we haven't put the social attraction in, but it's coming. Yeah.
So this is how it's working. So you begin with like ants, the random decision variable 1 level, they're moving around, and only if they find the food do they have to undergo this process, because if anybody who's stuck in between still does not lay pheromone. So pheromone is laid after the finding of food, right?
Well, this is, so I guess I should indicate that this is kind of a directed acyclic graph. Like they always start at the nest, they always move downhill, there's no way to go back up. And so this food, this is kind of just like to help the narrative, that there's a nest and there's food, but don't worry about that.
Because unless you, in this narrative itself, unless you find the food, you cannot compute the value of your optimization objective before you actually reach there.
Right, but in this case, you're kind of, all the ants in this world are going to be lucky enough to, as long as they can go from decision variable to decision variable, they're always going to find the food, and they always will be able to. This is sort of assuming that ants have this giant combinatorial options for getting all of these are feasible options. So these ants don't need to find a feasible option. All are feasible, they just need to pick among them.
So as and when they go from V12 to, let's say, V21, they will lay the pheromone there itself.
They lay the pheromone on both of these. Well, they go all the way down through. So that's, what you can think of is they come down, not laying pheromone, find the food, evaluate the function, and then come back up and lay pheromone when they get back to the nest.
Yes.
You can think of them laying pheromone on the way back.
On the way back.
Right, if that's helpful. So, like, if you can think of, they evaluate in this direction, and then they only lay pheromone on the way back. So, yeah. It's the reinforcement only comes on the way back.
Professor, could you describe what C means?
Concentration. So that's the, so this is the, or amount of chemical.
And also the function, the optimization function is the same for all the ants?
Yeah, in this case, you can imagine this being, and I'll say this is, F is optimization function. And assume here that F is greater than or equal to 0, and we're minimizing F. And Q is a hyperparameter, which is also greater than or equal to 0, well, greater than 0, strictly greater than 0. And you can, in this case, assume that all the ants have the same one. You can imagine cool extensions of this where you do multi-objective, kind of like Vega or something like that, where each ant has a different objective function, but they all are attracted by these pheromones. And so in that case, one ant is going to say, no, I really like this path, and another ant's really going to like this path. And maybe you end up getting the stabilization of multiple paths, which correspond to some Pareto frontier or something like that. You could imagine going down that route, so to speak.
Yeah, that's silly to ask, but do they remember the path in which they've come into this?
The virtual ants, they know nothing. So you can imagine the virtual ants, the virtual ants, you can imagine that yes, they do remember the path, but then once they get back to the nest, they forget. So there's no memory that way. Real ants are more complicated than that. But for the algorithm, you can think of that, yes, they have memory in one direction, they explore in one direction, commit to memory, come back and reinforce in the other direction, and then forget, and then start a whole thing over again. Okay.
We remember only the best path kind of thing?
Well, you just remember the path you took. So you took this path down here, you reinforced back up this way, and then you get here and you forgot. So you don't remember. Now we're going to get to particle swarm optimization where you do remember the best path over time. But in ant colony optimization, the hope is the chemicals are the memory.
Okay.
There's a question over here.
Yeah,
Okay.
So basically the shared memory here is nothing but the concentration which is being laid by various different agents on the same node.
Exactly, right. Yes, this is a distributed, again, the spatial complexity of this is such that we assume we have a bank of memory that we can put a state variable of sufficient resolution on each one of these nodes. And then that becomes a shared memory that everyone can access. It naturally decreases, so there is some other agent that we're not seeing here that is managing the shared memory, causing it to naturally decrease. And then on top of that, each individual agent is coming back to it and adding to it. So you can imagine that in a computational architecture, if you're implementing this and you really wanted to make this distributed and decentralized, you're going to have some issues, and that you need to say, well, then how am I going to implement this shared memory? So even though these swarm intelligence algorithms have a distributed component to the narrative, the implementation is often going to be centralized because they make use of things like stigmergy, and it's really hard to get, stigmergy kind of counts on, if I make a modification to this thing, everybody else has got to get access to it pretty quickly. And that is going to create sort of a central point of failure to these algorithms. Yeah.
How do we exactly calculate the optimization function?
With this, we just assume that we take each one of these things in. So this is, each decision variable gets bundled into the decision vector, and this was just calculated the same way we do into genetic algorithms. So I give you an optimization function, which might be, for example, let's say it has to do with the amount of time, this really could be a shortest path problem. And so it might be that I'm trying to get from Tempe to Columbus or something like that by driving in that direction. And these are all the cities that I could possibly go to. And so I say, well, I'm going to go to Tucson first, and then I'm going to et cetera, et cetera. And then after you go through the entire thing, you can say, well, how long did that take me? And then that could be my optimization function. So one of the first applications of this was actually solving shortest path problems.
Professor, the concentration function in the next time step will depend on the sum of the changes in the concentration. Sum of the del concentration term of all the ants, and then it's gonna we're gonna have to execute it for all the ants, and then we can go into the next time step.
So the beauty of this is that in principle, you actually don't, I'm showing this in a synchronous framework where I do need to gather all of these up for this kind of time step. But in reality, this can actually be implemented in an asynchronous way as well. So I could have a shared memory somewhere in my computational architecture, and I could have each ant walking on its paths asynchronously. Some could go slow, some could go fast, or whatever. And as long as they can hit that memory, then it doesn't matter if I'm doing this computation at once or if it's accumulated over the cycles. Yeah, and that's actually more like ants. Ants don't sort of all collectively go out and then say, everybody ready? And then collectively come back. But so you definitely could have each ant move back and forth. In fact, as you can imagine, if ants all went out and then shouted to each other through some other communication modality and then came back, you can imagine how that would change the dynamics here. So a lot of people, mathematically, it can be, in some ways, you imagine it dealing with asynchronous algorithms can be more complicated because we've been taught that clocks are a good thing to have when we write algorithms, but actually in a lot of these types of things, asynchronicity is actually a good thing. It makes it easier because it provides information, it leaks information to you in a smoother way. Whereas if everyone goes out, you've not accumulated any information. So when they all come back, they're going to start accumulating their information, but you didn't if you just had them going back and forth, then you could slowly build up information, and then gradually the new ants that were going out while some were coming back could make use of that information. So it can actually speed things up sometimes to have asynchronous agents accessing shared memory as opposed to synchronous agents. So that's sort of a higher level, more advanced topic. But I'm just hoping you can kind of think that through. All right, so questions about this before we get to the social part? Okay, so the social part is just how each ant chooses among these things. And so the thought is here that, that each ant is going to just flip a coin, or roll a die, roll a D1-sided die, and that die will gradually become biased along the highest chemical concentration. So to generate moves from one variable level to another, then we've got this, say, probability ID, which is going to involve, there's going to be a couple of new parameters here, but I'll start out by saying what you might imagine is a little obvious. I'll do CI K from K is equal to 1 to VI of alpha. And I'm going to add another parameter on the numerator and denominator here, so heads up for that, but just to motivate this is, okay, so what this is going to be, what is the probability that I move? Like, I'm sitting there at the previous decision variable, and I'm looking down at all of the other levels for the next decision variable. And the question is, what is the probability I'm going to go to any one of those particular levels? And what I'm going to do is I am going to look at the concentration on all of those candidates for my next step. And I am going to take that concentration and divide it among the sum of those concentrations. So initially, this is going to be a uniform choice among all of these options. But as one gets more chemical on it, it starts pulling more of the attraction to that. So this is the basic idea. Well, this is the you could view this as like a soft max or something like that, but the idea is this is a probability. So I'm going to draw my next, so I'll just make sure this is probability of moving to I, D. So in my map, in that previous section here, the probability, I'm sitting on the previous coordinate, whatever, I minus 1, and what's the probability of going to the next coordinate, and it's that. And, but I want to give myself a little more freedom, so I'm going to create, whatever this new, the eta or whatever here. And so this gives me, so you can think of alpha and beta as just shape parameters. And you can think of this eta coefficients as kind of like Bayesian priors. And so these are heuristic values to bias selection based on past experience. And so it's a way to kind of preload things or bias things to move in one direction over another. Eventually the concentrations can become large and dominate these things, but it provides kind of a time constant or something like that. You can think of it as a way of scaling each one of these concentrations by this other coefficient, so that a concentration, you need a much higher concentration on one level in order for it to gain the attention than maybe another level. And so it just, most of the cases you could, if you don't have any prior information, you could just set these things equal to 1, and then it's just this simple roulette wheel selection. But otherwise, this allows you to kind of bias the selection. And that's how we aggregate our social information in our ant colony optimization. They start out uniformly picking to the next levels and gradually start picking the one that everyone else has reinforced. And so I could write pseudocode for that, if that would be helpful. But let me see before I change. Is there questions about this? Yeah.
Yeah, so essentially, eta is the bias for based on the past experience of an individual land.
Well, you can. This is like more like your past experience as the designer. So you can, because this probability is not defined per ant, at least in this basic algorithm. This is defined per node, per island. And so, as you a designer, when you set this whole thing up, you might say ahead of time, I'd like you to. I don't actually want you to uniformly search through the space. I'm going to give you the option of checking out these things, but I really want you to focus your search here to begin with. And you can bias that by choosing these things ahead of time.
So doesn't that destroy the chances of exploration?
It reduces
if you're not
that.
giving an individual land wise option.
Well, the idea here is that you have a good idea that they're always going to find, or maybe you're only interested in a particular area, but it's difficult to say what that area. Maybe you don't want to have a hard constraint where you want to get rid of some levels. Maybe you want a soft constraint, or maybe in this framework it's just difficult for you to write your hard constraints. And so it's just a way to shaping the initial search so that they bias it in one part of that map instead of going all over the map.
Also, maybe we can make it a bit complicated by just decaying the beta term with time, and like it's gonna.
Sure, you could do extra things where, like, yeah, initially the past experience matters, and then over time it doesn't matter. So yeah, absolutely, you could do something like that. You have a question too?
How the algorithm accommodates change in the location of the food?
Well, so again, the food here is kind of just assumed to be this fictitious thing that doesn't ever move. So the algorithm is simulating ants getting from one nest to one piece of food. Now, to your point, one of the downsides of this algorithm is if you do change the objective function, f, during, like, so if you're moving around here a lot, you might imagine that it might take a while for your algorithm to settle down. And it could be that you have a time varying optimization function. You actually don't want to optimize, you want to track. So maybe there's a best path, but then the best path changes over time. Now, a downside of this is you can get locked in to old paths if the concentrations are really high. And so there you may have to make modifications to the algorithm to allow for more dynamism. But in this case, we sort of assume the fictitious food is always in the same spot. It's just equally accessible from all of these decision variables, and we assume that the optimization objective is one. There's just constant over time. Yeah?
Yeah, so you did talk about a more dynamic nature of this algorithm where some of the decision variables are deleted in, I suppose, the run of the program.
Well, that's one. Yeah. So I mentioned that, and I'll mention that in a second here. There can be paths that are suddenly made non-feasible, and what we'll see with this algorithm is that one of its noted strengths is that there will be like so imagine of these m ants, there might be n-5 of them that are going down the optimal path, but there will be the other ants will be going down some other path. And that other path is often the second best solution. So if suddenly you cut, you say, all right, this isn't available anymore, your n-5 ants now have to start searching. But while they're searching, the other 5 ants are sitting here at the second best path, giving you an alternate way. So it allows you to quickly switch to a second best solution and even a third best solution.
So my question was, when will this happen? When will you suddenly run out of choices in, I suppose, the middle of it?
Right, well, yeah, that was sort of, it was booked as a potential. So you can imagine there might be a very small set of problems where suddenly a decision variable set of levels becomes unavailable. So like physically you can imagine, like whatever rock that they were crawling on gets kicked, and so that rock's not available anymore. And so that's kind of, I think, was motivated by like, well, in principle, if you are living in some world where you have to solve an optimization problem where an option for decision variable 2 could disappear, then this would have a way to solve it, and you wouldn't have to redo the whole problem. Whereas if you just used a conventional optimizer, you'd have to kickstart the whole optimizer again. You wouldn't even have a place to warm start the thing. And so in this case, you kind of already have the second best solution that's been kept there. And maybe actually, having a ranking of solutions will be good for your stakeholder, because your stakeholder might say, okay, I understand why this is the best solution, but it turns out we actually are not allowed to do this or combine this and this together. So even though we said you could have this level and you could have this level, we didn't think you were going to combine those levels. And so this is not feasible. And then you'd say, okay, well, we have a second best. What do you think of this solution? And then say, that's fine. Question over here? Okay, all right.
So, Professor,
Yep.
you mentioned eliminating decision variables. I think you meant eliminating one of the states of a decision variable.
Right, the levels of a
Yes.
decision variable.
One of the states.
Right, yeah.
But if you eliminate all of them, then it's probably a cutoff thing you can't go ahead.
Right, yeah, that would not use, you need a way to get a path from here to there. And once you do all of that, then that effectively turns, they have to research, you have to have a way to jump from here to there. That's a major topological change, sure. All right. Okay, so you can imagine a basic pseudocode for this is you just start out with your M population size and your N decision variables. And then you've got this D sub I values for each variable. And so with that, you're going to need to initialize, so I'm going to leave out details here, but you're going to need to initialize your concentration matrix. So keep in mind that memory footprint there. And then generate M initial solutions. And you can do that randomly. And so you can think of these, these are these M ants that have sort of traversed the graph, but they had no prior information, so it kind of, it's, so you're basically just generating M decision vectors. And then, so while not whatever your termination condition is, you iterate over your N levels, or your N variables, and then the D levels, update your concentration, I comma D, evaluate the probability, PID, and you can cache that. So that's another, you can just store that somewhere, so that's another piece of memory you have to worry about. Next. And then from here, we do the social stuff. And so we've now iterated over the graph, and so now we iterate over the ants. So for I is equal to 1 to M, we'll say, I'll say for J is equal to 1 to N, select value based on P, and I guess here I have to do J comma D the way I've written that. Next J, next I, end while. And that's basically it. It's a relatively simple algorithm that is just allowing ants to crawl over a graph and add update concentration. So you can basically imagine that what's happening here is you generate a whole new set of decision vectors, and then at the top of this loop, you evaluate fitness here, and then you provide probabilities to choose the next set of decision vectors. So the fitness evaluation is happening here. And that is the reason why we have to generate M solutions randomly initially. So it's almost as if we let the ants go out and come back, and then that kicks off the first fitness evaluation, which then rebalances the probabilities, generates the next set of paths, and then redoes the whole thing. So questions about that implementation? How we are using a decision vector to encode a path taken by an ant from nest to food. All right, so the strengths of this, as I already mentioned, it keeps the second and third of your best solutions around. And so it also naturally maps to real routing networks. And the fact that it keeps that second and best solution around allows you to think about failures of those routing networks. And so you'd say, well, when would a decision level just disappear? Well, maybe that decision level is choosing the next router. And so I could say, I've got a huge, I'm at this particular router, I can route this packet through this router, or this router, and so I can now do real-time routing with a kind of a version of ACO, maybe implemented with some distributed, so this concentration matrix, in principle, you might be able to implement it in a distributed way, where you don't actually have to have all the memory in one place, but you need sort of each cell to be accessible at particular times. And so you could imagine implementing this on a real routing network, and then if a router got shut down, you wouldn't have to then re-optimize. You immediately have the second best solution will very quickly draw the attention of all the ants to it, and all the packets will go down that way as well. So it does map very well to routing problems. So optimizing during real-time routing. And I have seen people publish papers in the transportation community about implementing ant colony optimization on transportation networks, trying to give people suggestions of where they should go at particular times of day. It's rush hour, maybe you shouldn't go take the highway, you should go some other way. A lot of times, for simplicity, people radio back to a central computer that runs ant colony optimization and then sends the recommendations back to those big screens that tell people that, oh, there's a huge delay on the left, maybe you should go to the right. Now, it would be cool, but again, I think because people worry about guarantees and they really want all the computation to be in one place, to actually implement a physically embodied version of this on a highway system where cars are laying virtual pheromones along the roads. And so you could do that, and then the dynamics would be directly tied to the dynamics of the cars. But I think it would take a lot more infrastructure because you actually, right now we have a lot of the ways to bring info back to a central computer, but we don't necessarily have ways to store it in the streets. But you could imagine implementing something like that, and maybe in infrastructure systems of the future where we have a little bit of memory available that's peppered out throughout all these ubiquitous computing devices and IoT, that you would be able to do that. So a lot of opportunities for taking this into the physically embodied realm, but I think few people do that. There have been some robotics cases where people actually have built robots that smear alcohol on the ground and can sniff up the alcohol. So they've got alcohol sensors on them, and it seems to work. There are other cases where people have done virtual marks, but the decay function is the hard thing to do, because if you just have to drag a marker, you can attract things to it, but the marker never goes away. So you need to have some way of getting rid, and that's kind of a necessary part of these algorithms. You have to have a decay function.
The alcohol evaporates, right?
Pardon me?
The alcohol evaporates, right?
That's exactly right. That's what makes it work. Yeah, right. But it turns out that robotic olfaction is crap, so there aren't really any good chemical sensors for robots. There's some that they, the very, very expensive ones that they use at like TSA and all those are still just not very good compared to like a dog or a moth or a bee or an ant. And so we are nowhere near the device level where we can really make like true kind of chemical communication work as well as this. But definitely in the lab, you can do this with alcohol. Lots of people have. Yeah.
I'm just wondering if you could leave digital markers some way.
Sure, digital, virtual pheromones, there's a whole literature on that. And so but you need sort of a way to lay those virtual pheromones down.
Signal generator.
Right, some people do things like a robot carries another robot on its back, and you can imagine, so that if you lay down something and then that thing can eventually go home, and that's like your decay function. So you can come up with other ways to do this, but they kind of will end up kind of approximating the dynamics here, and then you have to really, you have to run a whole new set of experiments to see how they work. So that's the end of ACO. So any other questions on ACO before we move on to the next sort of thing inspired by ACO? Yeah.
So how do you choose a decay factor?
Good question. So that this row that originally here is this is like an exploration and exploitation trade-off, you know, and so this sort of depends on how much you're willing to trust your kind of your memory, or it's sort of how much do you trust the others? Because really, what this decay factor is, if it doesn't decay, that means that you're saying everyone should listen to everyone else's past opinion, and so that is going to vary with your optimization function. So it's unfortunately one of these hyperparameters where you almost need a hyperheuristic to optimize those. So, but you could imagine that, you know, there are two low values. Like if you set this to 1, then you're not going to get any social information, and that's obviously bad. If you set it to 0, it's going to be like that marker case, and initially it might do some interesting things, but then over time, then you just get convergence to, it's like genetic drift, basically. So there's like, I would actually think of this more as that drift selection sort of trade-off there, and exactly where it's supposed to be, I think is going to depend on the optimization function. But start with, you know, I would start with something that make the decay here small, like a row of 0.7 or 0.8 or something like that.
But then would it be more biased if you have a small decay factor?
What I meant, so the K factor I guess would be large, so the 1 minus would be small. So I say make it, initially I would say try to make it decay, you want to be more like the quick evaporating alcohol than the non-evaporating marker. So start with the alcohol and gradually sort of change the humidity and temperature in the room so the alcohol doesn't evaporate as quickly. Yeah, and so that's the other cool thing about ants is that, so ants that lay trails have something like this. It's a little more complicated, but it turns out that they are persistent branching networks, which are formed by a process that's like this, change as you move them into an environment that differs in, say, humidity and temperature. And that all goes back to this idea that you can predict those changes by figuring out how that's affecting the decay rate of their pheromones. So it is this nice, interesting coupling between their communication and their environment. And that's the reason why a dominant strategy in one environment may not be dominant in another, and vice versa, because this decay rate is effectively being set by the environment. For an algorithm, it's set by the programmer. And so you can imagine there are opportunities to adaptively change this as well. So you might notice that, you know, we're not really converging, so let's affect this decay rate so that maybe we get convergence. And that's going to be, you know, more like adaptive step size. All right. So where we're going to go next with this is, so the two other categories that I group into this kind of lecture are bacterial foraging optimization, which is another way to make use of chemically driven social information, but it allows us to solve a wider range of optimization problems. And then after that, we'll talk about so-called particle swarm optimization, which both ACO and PSO have been very successful and again are implemented in most major optimization type packages, and you can find APIs for Python and all the rest of other things. Yeah.
Were you planning on putting some readings up for Unit 6? It's empty.
Oh yeah, sorry about that. Yes, I can, again, in the switch from Blackboard to Canvas, I haven't populated all that yet, but yes, I will put up readings on these things here. Yeah. But rather than get started on that, are there any other questions? And then we can pick up with this next week.
2 weeks.
2 weeks, not next week. Yeah.
Yeah, so if you talk about the strengths, any weaknesses of ANCOR?
Oh, well, I mentioned like there's, you know, this dynamic issue, like dynamic optimization. It's designed for discrete optimization, although if the guest speaker comes in, he'll talk about how he turned it into a continuous optimizer as well. So, yeah, I mean, you can come up with a lot of weaknesses, but it's sort of easier to sort of think about, like, you know, where its strengths might come from. But then a lot of the other weaknesses are going to be shared with, you know, could it get caught in local traps, and so yeah. And then of course, this is the very basic ACO. There are more derived versions of ACO that hedge against these problems. Any other questions?
If you turn it into a continuous value problem, how do you distribute the configuration or calculate the probability in that way?
Well, I'll leave that as a suspenseful. I'll leave you in suspense for that, so you can think about that. And again, then I'll let our speaker chat about that. All right, thanks, guys.